Hey guys, welcome to section 3.5. So this is not a typo. We are ending the chapter with 3.5. It deals with limits. So we thought it'd be a great idea to include it in our unit 1, which also deals with limits, instead of waiting to chapter 3. Okay, so just to review with you what we did before. So let me write this before we even get to this problem. We were looking at, let's say, this problem, the limit as x approached 0 from the right of 1 over x. We did this yesterday in section 1.5. And we said, if we had a graph, of course, we'd look at it. We don't. So what number is right to the right of 0? Isn't it super small positive? So if we have 1 over super tiny number, that's super huge, and we got infinity. Now, what did that mean? That meant that 0 was a vertical asymptote because we got infinity as an answer. Okay, so when we were dealing with this, we would say x equals 0 is a vertical asymptote. I just don't want you to confuse the two, vertical and horizontal. So this is what we did yesterday. This all is from section 1.5. Okay, and that's how we identified vertical asymptotes. Now notice that infinity is the answer in this problem. So infinity is what we get as our answer. The x that we're approaching, that value, which is 0, is your vertical asymptote. Today, what we're going to look at is horizontal asymptotes. So a case that this comes up, so here's an example up above. It's saying, before we looked at x going to c, that's what this case is. Now today we're going to look at x goes to positive or negative infinity. I like to think of these as like, what happens over time? So this example, as time passes, hot coffee will cool until it reaches room temperature. For those of you who are coffee drinkers, I love my coffee super hot. So after like 10 minutes, it's almost too cold for me to drink already. And you can see here, right, it starts out hot, and as time goes on, it's going to level off until it gets room temperature. So can you see right here your horizontal asymptote? This is completely different than a vertical asymptote. Okay, so this, just to show you the difference again, horizontal, x is going to plus or minus infinity. In our examples that we did yesterday, we got infinity as an answer. Okay, if you look right here in this box, I'm describing horizontal asymptotes, and it's as x goes to positive or negative infinity, this is your horizontal asymptote. Okay, so infinity is in different spots. Horizontal asymptotes, again, are what happens over time. Okay, I also thought it might be helpful just to look at a side-by-side of both of them, especially since we just went over it yesterday. It can be a little confusing. So on this first example, I want to just focus on horizontal asymptotes. And then on the next one, we'll look at just the vertical. Okay, horizontal asymptote, you guys can see it right here. Let me get yellow. That's a really wide asymptote. Okay, so you have the horizontal asymptote there. So what does that mean? Let's write out the limit. Now, they told us up above that horizontal asymptotes are such that x goes to plus or minus infinity. If a problem asks you to find horizontal asymptotes, that's really code word for find the limit as x goes to plus or minus infinity. So first, let's look at x going to infinity. Let's call this graph f of x. So what this is saying is what happens over time. So as you go all the way to the right of the graph, what happens? So as you go to the right, do you guys see we approach this 3 value right here? So our answer here would be 3. A common mistake is that you forget to check what happens as x goes to negative infinity. So let's not fall into that trap, and let's check it. So as we go to negative infinity, that means we're going all the way to the left. What happens? Do you see that it also levels out there? That does not have to be the case. It just is in this problem. Notice also that this graph crossed the horizontal asymptote. Is that legal? Is that allowed? Of course it is. So the graph can cross horizontal asymptotes. Okay, that's going to be okay if that happens. And we'll look at why it's not okay in the next case. Okay, so horizontal asymptotes, again, we're looking as x goes to either positive or negative infinity, and the value that we get here is our horizontal asymptotes, and it is completely legal for us to cross them. The next case I want to analyze the vertical asymptotes and kind of compare and contrast with these guys. How do you guys find vertical asymptotes? Do you remember vertical asymptotes are found where you get infinity as your answer? Can you see by looking at this that these are your vertical asymptotes? So your vertical asymptotes are x equals 2, x equals negative, or I'm sorry, x equals negative 2 and x equals 1. So how would we prove those? Is we would say, well, the limit as x approaches, right? If you look at the graph, it looks like a negative 2. We're going to look at negative 2 from the left, and then we're going to look at the limit as x approaches negative 2 from the right. So as you approach negative 2 from the left, you go to negative infinity, negative 2 from the right. Let's move the graph down a little bit. Negative 2 from the right, you go to positive infinity. So let's go ahead and write those down. We said from the left was negative infinity, and this was the right. Before we go on, remember the definition of vertical asymptotes. It's when you get infinity as your answer, and the number you approach is your vertical asymptote. If you compare the highlighting with this one, you can see that the numbers and the infinities are in different spots. Okay, going on now, we also said, well, it looks like there's one at 1. If we take the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right. 1 from the left. Here's 1. 1 from the left goes to positive infinity. 1 from the right goes to negative infinity. Let's write that down. So 1 from the left was positive, right? And then this one is negative. Again, we know these are vertical asymptotes because we're getting infinity and negative infinity as our answer, and those are your vertical asymptotes. Okay, so side by side, I think really helps to clear it up. Another note that I want to make down here is that vertical asymptotes are not, see if you know what I'm going to say here, are not included in what? In the domain of f of x. The graph cannot cross them. The graph does not cross the vertical asymptotes. Okay, completely different than the thing we saw on the left, where we could cross the horizontal. Remember, the reason we have vertical asymptotes is because there's a domain restriction. So that's why we can't cross it, because the function doesn't exist there. Like at negative 2 and at 1, the function doesn't exist. Okay, so hopefully that helps to clear up any confusion if you had any between the two asymptotes. Let's answer the next couple. Okay, so that's the idea today. Now, as always, we'll go through some examples. Look at the way I have this set up. Look at A and D are the same. One's going to infinity, one's going to negative infinity. We're going to sketch the graph and then talk through these. So here's the graph of sine x, right? And then it goes on and on and on forever. So talking through this, as x goes to infinity, that means as you go to the right forever, what happens? Well, look, if I keep going to the right, it just keeps going and going and going. It never levels off. Whereas you look at the one we did up here, as we went to the right, it leveled off at 3. So if the graph does not level off, then the limit as x approaches infinity does not exist. D, underneath it, what this says is as I go to the left, what happens? The graph still doesn't level off. That limit as x approaches negative infinity also does not exist. Okay, do you guys remember the next graph, 2 to the x? This is exponential growth. So what happens as we go to the right forever? That's what this infinity means. We're getting bigger and bigger and bigger to the right. As I go to the right, the function also goes up forever, giving us infinity as an answer. The next problem underneath it says, what if you go to the left forever? Now look, as you go to the left, we're leveling out. What do we level out at? At 0. Y approaches 0. This next function you can think of as, remember, 2 to the negative x is 1 over 2 to the x. So we're going to look at the graph of the decay, but if you didn't have the graph or didn't know it, you could also deal with this function. It might be a little easier. Okay, so a decay, exponential decay looks like this. As we approach x, as x approaches infinity, so as x gets huge, what happens? We go to 0. And then on the left, this is saying let x go to negative infinity, and then we go up to positive infinity. Okay, so just a quick look at the graphs and horizontal asymptotes. Okay, the next couple. Limits of infinity at a rational. So the idea behind this is as we take the limit as x goes to plus or minus infinity, you're going to divide the numerator and denominator by x to the m, and do you see that right there? So we're going to divide by the, like if there was x to the 5th on the bottom, we're going to divide everything by x to the 5th. Okay, that's what all this means. A shortcut, and this is probably what you learned last year, is if you have something bottom heavy, meaning the degree in the bottom is the largest, then you are going to get infinity as your answer. If you have something top heavy, so let's say you had an x to the 5th over x cubed, you're either going to get plus or minus infinity. If they're same, so if the if the power appears in the highest power is in the top and the bottom, then you do all of this stuff, which is kind of a lot to highlight, but it's the coefficient. And this probably sounds a little familiar to you. As we go through it, you'll see. Okay, example 2. And guys, this is it. This is just this page today. So awesome last day of the first unit. Okay, as x goes to infinity, so thinking through this, x goes to infinity, we have 4 over a huge number, right? What's 4 over a huge number? Try to picture what that is. It's a super small number, so small that we're not even going to count it, and we're just left with 6 as our answer. Okay, going on to the next one. The shortcut said, it was number 3 of the shortcuts that we just looked at. So it was this one right here. It said if the highest power is in the top and the bottom, then we take a ratio of the leading coefficients. So I'm going to tell you that looking at this has x to the 1 and that has x to the 1. The coefficients in front are 5/3, so that's our answer. And then we're going to look at y. Notice in all of this, I don't want to leave out that x is either going to infinity or negative infinity. These would represent horizontal asymptotes. Okay, so what's happening here is if you look again up above, this was the shortcut part. This is this first part is actually what you're doing. It says to divide by the largest degree in the denominator. So this would read as the limit as x approaches infinity. The largest power here is x. So we're going to divide everything by x. So 5x over x is just 5 minus 4 over x. 3x over x is 3, and 6 over x is 6 over x. Now, the reason that the shortcuts work is because look what happens here. If you have 4 over x, and x is huge, 4 over a very big number is teeny tiny, so much that it's irrelevant. 6 over x, again, goes to 0, and that's how you're just left with this 5/3, and that's why the shortcut works. Okay, going on to the next one. Do you guys notice that we're tied here? So it's a ratio of the leading coefficients. What should your answer be? 4. The reason would be if you divide everything by the largest power in the bottom, you get 4 over 1 plus 1 over x squared. 1 over x squared goes to 0, and you're left with just 4. Next one, looking here, you're comparing powers. You're comparing the largest on the top, which is a 4, to the largest on the bottom, which is a 9. This is bottom heavy. Looking at your shortcuts, bottom heavy is right here, and you're going to get 0. So our answer here is 0. If we're looking at y, we're dividing everything, because we're approaching infinity, by the largest power in the bottom, which is x to the 9th. So this is going to be 6 over x to the 5th minus 8 over x to the 8th plus 9 over x to the 9, all over 5 minus 7 over x to the 9. So we divided everything by x to the 9. X is getting huge. X is going to infinity. So 6 over huge is gone, 8 over huge is gone, 9 over huge is gone, and likewise, what are you left with on the top? Nothing. So you're left with a nothing over 5. Nothing over 5 is 0 over 5, which is 0. Next one, I think we have the same problem. No, we don't. Never mind. Okay, on the next one, we're going to negative infinity. Now, if we're comparing degrees, powers, we have a 9 over a 2. If you look up above again, this one is top heavy. So we're either going to get a positive or negative infinity. Okay, so we have to explore this one. Okay, so on this one, we're going to divide by the largest power in the bottom. So we're going to get the limit as x goes to negative infinity. We're dividing everything by x squared. So we're going to get 6x to the 7th minus 8 over x plus 9 over x squared, all over 5 minus 7 over x squared. Because x is getting huge, anything with 9 over x squared is gone, 8 over x, because a number over a huge number is irrelevant. Now look what we have. So we're left with these pieces right here. I know we technically can't work with infinity or negative infinity, but think about what's happening. We have a super huge number that's negative. If you raise it to an odd power, what's a negative to an odd power? Isn't that still negative? So what we have is a 6 times a huge negative. So what we really have is a huge negative number up top divided by itty bitty 5. So that is still a huge negative. Another way to look at it, because remember the shortcut said that if it's top heavy, that we're either going to get plus or minus infinity. One way I look at it is if I'm just focusing on these, because those are the powers that I have. 9 over 2 is 7, which is odd, and a negative raised to an odd is still negative. Okay, on the next one, we're going to divide, well, it's top heavy, so we know it's either plus or minus infinity. If we divide everything here by an x to the 4th, we're going to get 6x squared minus 8 over x cubed plus 9 over x to the 4th, all over 5 minus 7 over x to the 4th. Remember, x is going to negative infinity, so anything with a number over a huge number goes away. Now look at what we have. X is going to negative infinity, which makes this 6 almost irrelevant. So if I have a negative number and I'm squaring it, it's now positive, and that's how we get positive infinity. And let me go back and write the answer here. Okay, another way, again, I would look at it is I would say that this is top heavy. Because it's top heavy, it's either going to be plus or minus infinity. 6 over 4, you would subtract exponents and get x squared, and a negative squared is a positive. Okay, going on to the next one. Okay, G is looking really messy. If we look at the top here, we have a 3.5 and we have a 2. 3.5 is bigger, top heavy, plus or minus infinity. Let's divide by the largest power in the bottom, which is an x squared. So that's going to give us the limit as x goes to infinity. X squared is x to the 2, so I'm going to have 9x to the 1.5, which I'll call 3/2. So what I did there is I'm looking at this as 3.5 minus 2, which is 1.5. Minus 3, remember we're dividing, so what I really have is x to the negative half over x squared. So that's x to the negative 1/2 minus 2, which is x to the negative 5/2. Okay, so that's how we're getting this piece. We divided by x squared, so that's just 1. And then over here, let me erase this. And I'm going to use that spot to work again if you need to see it. Over here, we have an x to the 1/2, and we're dividing everything by x squared, remember, because that was the largest power in the bottom. So we have this over x squared, which is x to the 1/2 minus 2. So 0.5 minus 2 is negative 0.5, negative 1.5, and negative 1.5 is 3/2. It's hard to deal with limits when you have negative exponents because what we want to see is a number over x if we can. So let's rewrite this as 3 over x to the 5/2, 1 minus x, 1 over, let's erase that. One sloppy work here. And then we'll have 1 over x to the 3/2. Okay, just checking this over. You know what? I see a mistake real quick. This was a plus in the beginning and I just accidentally wrote a minus. So let me just fix that. It's not affecting. Hopefully you guys caught it. Okay, now x is going to infinity. X is getting huge, guys. So right here, 3 over a huge number, gone. 1 over a huge number, gone. Look what we're left with. X to the 1.5, this is still growing. So we are going to have infinity. Okay, if we are looking at largest exponents, trying to use the shortcut from the beginning, we are comparing 3.5 to 2. What's bigger? 3.5. So it's top heavy, which means we get plus or minus infinity. We're going to positive infinity, we'd get a positive infinity. Okay, now on the next 3, look at them. Do you see the square roots in the denominator? We haven't had that before. So a little background before we jump into this problem. I'll write it right here, and I'm going to write it in blue. Okay, the little note to you, as promised in blue, is when you're taking square roots, if you have a positive x, so if you know x is greater than 0, then x is the square root of x squared. Easy enough. However, if x is less than 0, then x is the opposite of the square root of x squared. Okay, so we'll have to keep that in mind as we get down to I and j. Right now, in h, I think we're going to be okay. Okay, so what we're going to do is we want to be able to compare degree of numerator, degree of denominator. Remember, the idea is to divide everything by the largest power in the bottom. So that's what we're going to start with. But we have this radical. So we're going to start by factoring out an x cubed. So we have x squared, and then we have x cubed. Let me fix that. If we factor an x cubed out of the bottom, I'm going to have 1 plus 4 over x cubed. Okay, so I'm trying to compare power of the top, which is the numerator, power of the denominator. To do so, I'm going to factor out an x cubed in the denominator under the radical. Okay, now what I have, well, the reason we're doing this is here I have 2 terms. Here I don't, but I have 2 things being multiplied. So I can apply the square root to each of them independently. So the limit as x goes to infinity of x squared. Now the square root of x cubed is going to be x to the 3/2. And then I have the square root of 1 plus 4 over x cubed. Okay, remember here, or not remember, but just note, we have 2 terms being divided, or 2 x's being divided. We can subtract their exponents. So now you have x squared over x to the 3/2. How about we think of 3/2 as 1.5? So 2 minus 1.5 is 0.5. Now remember, x is getting huge, guys. As x gets huge, 4 over huge is 0. 1 plus 0 is 1. Square root of 1 is 1. So now I essentially just have this. So think of the function x to the half, or just think about x to the half. As x gets big, so does x to the half, and we end up with infinity as our answer. Okay, going on to the next one. Look at I and j. They are so similar, except in one x goes to positive infinity and in one x goes to negative infinity. So we're going to start off by rewriting this. Now in this case, this one looks slightly different. Do you guys see here, as x is going, well, let me go back up here. I have an x squared here. I can rewrite this as the square root of x squared because look at, I know x is going positive infinity. So if x is going to positive infinity, x is going to positive infinity, that means x is positive, so that means I'm looking here. Okay, because x is positive, so for positive x, x is the square root of x squared. So because for positive x, x is the square root of x squared, I can replace x with the square root of x squared. Okay, now what we're going to do, we're going to try to move everything to the denominator here. So what I mean by that is if we divide the top by the square root of x squared, we'd have to do the same thing to the bottom, divide the bottom by the square root of x squared. So now we get 1 on the top, and we have x squared minus 4 over x squared. Now we can divide everything under the radical and get 1 minus 4 over x squared. Remember, as x gets huge, 4 over huge is 0, and we're left with just 1. This is a problem you for sure might want clarification on in class. We're going to do something super similar in J, so hopefully if there's any questions, you can clear them up here. We now have the limit as x goes to negative infinity. Okay, I can replace, now x is negative, we know x is going to negative infinity, so look up above at the blue again. If x is negative, I know x can be replaced with negative square root of x squared. So now I'm going to replace the numerator, which was x, with the negative square root of x squared, all over the square root of x squared minus 4. Limit as x goes to negative infinity, I'm just copying and that negative there. Okay, just like we did before, we're going to try to divide the top by square root of x squared, divide the bottom by square root of x squared. Anything divided by itself is 1, and then on the bottom we have x squared minus 4 over x squared. We can divide everything in here by x squared, so that's going to be our next step, and we're going to get the limit as x goes to negative infinity of negative 1 over the square root of 1 minus 4 over x squared. Remember, an x is going to negative infinity, so a number over a huge number is gone. 1 minus nothing is 1. So then I'm left with negative 1 over 1, which is just negative 1. So the side by side I think is helpful to see how these would work. And we are done with Unit 1. Good job, guys. Bring your questions to class. As always, see you later.